Well, so let me thank the organizers for inviting me to this very nice meeting, and also thanks all of you to come so early in the morning when the weather is very conducive to snuggling in the bed for some more time. So what I want to, so what I hope to tell you about is some studies I've been involved in for many years now, looking at very strongly correlated band insulators. As you know, the study of strongly correlated band metals, what I mean by that is something that would be a metal in the absence of correlations, has been occupied center stage for several decades now, especially after high Tc superconductivity. But studies of strongly correlated band insulators, something that would be an insulator in the absence of correlations, actually hardly been looked at, in relative comparison. And I'm hope by the end of my talk you'll be convinced that this is something worth looking at because there are lots of interesting possibilities here. Okay. And this work has actually been done in collaboration with it started actually in collaboration with Arti Garg and Mohit Renderia when Arti was a graduate student at TIFR and Mohit was just about on his way to OSU. And then after her return, she is a faculty member in Saha Institute and I'm continuing to collaborate with her. And recently, there's one of my students, Soumen Bagh, who is here in the audience, and Anvesha Chattopadhyay, who is Arti's student in Saha Institute, joined the effort. So this is some of the papers. I forgot to add an acknowledgement to the funding agency, Department of Science and Technology. Okay. All right. So begin with the motivation. Well known that strong correlations can drastically affect band metals. In particular, even for weak interactions, if you have nested Fermi surface, you induce spin or charge density wave gaps at the Fermi surface at half or commensurate filling. And of course, you have the Mott metal insulator transition, even in the paramagnetic state of the half-filled band, even if there is no ordering. And then high temperature superconductivity, anomalous normal state, pseudo gap upon doping. All these properties are supposed to be due to strongly correlated band metals. And the workhorse model is for looking at these has been the Hubbard model. And that was ever since the time of Anderson's remarkable suggestion that all the action in the cuprate superconductors is in this copper oxide layer, and the low energy physics of that is actually can be modeled by the strongly correlated Hubbard model. Okay, so just a brief reminder of how that works. So if you take La2CuO4 in band theory, it should be a metal. It should be half filled and it's metallic. But of course, experiments show that it's an insulator. And the idea is that if U is very strong in a real space picture, you'd prefer to have one electron per site. Then of course, that induces a charge gap. If these electrons try to move, they have to pay an energy cost U. And that's a charge gap. And the spins, depending on the temperature, can be antiferromagnetically aligned or paramagnetic, but it's an insulator for charge transport nevertheless. Okay, so the idea is that La2CuO4 is a Mott insulator and cuprate superconductors are doped Mott insulators. There's enormous amounts of experimental and theoretical work exploring this idea. But so now I want to talk about, how do strong electron correlation affect band insulators? You might think at first sight that nothing dramatic is likely, because crudely you can say U promotes localization of electrons, insulating behavior, it's already insulating, what's going to happen? So, and you might think that even doping is not likely to do anything because a small number of carriers in the valence or conduction band, so correlation effects would be weak. But I hope to convince you that actually dramatic things do happen when U is of the order of the insulating band gap. And the bulk of my discussion will use what is perhaps the simplest model of correlated band insulator, something called the ionic Hubbard model. I'll tell you about it for those of you who are not familiar with it at half filling, and a little bit mention with something about what happens when doping. And most of the studies that whose results I report use this approximation called the dynamical mean field theory, which maps lattice models to quantum impurity models embedded in self-consistent electron baths and approximate impurity solvers called iterated perturbation theory and continuous time quantum Monte Carlo. I actually won't have time to discuss methods and all, but if anybody is interested, I'll be happy to tell you the details. And some of the studies also use strong coupling Gutzwiller approximation, which I'll do. All right. So what is the ionic Hubbard model? It's basically you take the Hubbard model on a bipartite lattice and add a local staggered potential. That's what it is. That's one way to think about it. You take the Hubbard model, which is that, which I've shown you before, and then you have two sublattices. You put a potential delta on one sublattice and minus delta on the other sublattice. Okay, all right. Or you can think of it as this tight binding model with a staggered potential, and then add a correlation, local correlation term. Okay, so I'm going to be alluding to two versions of this model, which is the T ionic Hubbard model, where the Tij is non-zero only for nearest neighbor sites, and then the TT prime ionic Hubbard model, where this Tij is has a value T for nearest neighbor sites and a T prime for next near neighbor sites. And I'll be for the bulk of the talk, I'll be working at half filling, where the total number of electrons per unit cell is 2. And if T prime is 0, this is simply achieved by taking the chemical potential to be U by 2. And this model, for example, with U equal to 0, is the simplest model of a band insulator with a gap 2 delta. And the question I'm raising is, does anything interesting happen as U is increased? Okay. All right. So let's look at some simple limits of this model. For U equal to 0, the Hamiltonian can of course be diagonalized exactly by going to K space. And if I'm just sticking to the T model, I have two bands with energy dispersions just given by the simple formula. There's an upper band with a plus sign and the lower band with a minus sign. And you can see that there's a gap delta when epsilon k is 0, which happens on this square. I forgot to draw a picture. If you take the original Blount zone, there's the square, which would be the half-filled Fermi surface, right? There's a gap now. And at half filling, the lower band full, upper band empty. We have a paramagnetic band insulator with a gap 2 delta, actually it should be, or delta, charge gap from delta from the chemical potential, which is at the midpoint. Okay, if I take delta equal to 0, of course, that's the standard Hubbard model, and that's a medal for U equal to 0, and also in the, say, restricted Hartree-Fock approximation for any finite U. However, if you, for example, do unrestricted Hartree-Fock analysis allowing for magnetic order, you'll get an antiferromagnetic insulating state for any U with a charge gap which is U times the staggered magnetization. And the gap is the same for both spins. Okay. If I take the TU delta ionic Hubbard model and do Hartree-Fock, restricted or paramagnetic Hartree-Fock, you'll find that interestingly that the gap, effective gap, is actually reduced by U times the staggered density. That is the difference in density between the A and the B sublattices, because remember they have different potentials. So actually the gap decreases. So there's already a strange effect that the correlation effect is reducing the gap. But unfortunately, if you do this self-consistently for arbitrarily large U, the gap never vanishes. It's always finite. So you always have a band insulator for all U, even when once delta is non-zero. But new possibilities arise if you do methods that work better for large U, such as dynamical mean field theory. That's the thing. And you can see some of these possibilities by examining the atomic limit of this model, where I just turn off the T, where the correlation effects are really strong. Then let's look at these A and B sublattices sites, and then see what the states are. And then you can see that if U is smaller than 2 delta, on the A sublattice, the lowest state is the empty site, and on the B sublattice, the lowest state is the doubly occupied site. You can see that, think of that as the crude version of the band insulator, extreme version of a band insulator, where one sublattice is empty and the other sublattice is occupied, completely occupied. On the other hand, if you go to the large U limit, U larger than 2 delta, you'll find that on both sublattices, these singly occupied states are the lowest states. So this would be your Mott insulator. Okay, exactly when U equals 2 delta, within this atomic limit, these two states will become degenerate here, and these two states will become degenerate here. And then that allows the possibility of particles moving through the lattice. And you can imagine that if U minus 2 delta is of the order of the separation between these levels, I mean of the order of T, then certainly lots of interesting effects should be there. Okay, so to explore this, we did dynamical mean field theory, and the first surprising result back in 2006 that we found was that in the enforced paramagnetic state, or actually in the models with sufficient frustration, as I will talk about later in this talk, turning on correlations reduces the band insulating gap, and it actually vanishes. Remember, in the Hartree-Fock, I was telling you it decreases but never vanishes. But when you do dynamical mean field theory, you find actually it vanishes at a finite critical U. And so this is a correlation-induced quantum phase transition from a band insulator to a metallic phase. That was pretty surprising for us. And the metallic phase is actually stable for a narrow range of U. But if you keep increasing U, eventually the gap turns on again and increases as U increases, and that it becomes a Mott insulator. And here the picture of the gap goes to 0, stays flat, stays at 0, and increases. So this is the band insulator, a metal, and Mott insulator. So and that's the phase diagram we found, and it's kind of robust actually. We've done it for the beta lattice and the 2D square lattice. We plotted as a function of a ratio of the energy scales to the bandwidth. It's pretty much the same, not very different. I will tell you more about it. It's kind of within within dynamical mean field theory, it's generally, you get Fermi liquids basically. But I want to suggest that there are interesting possibilities that it could be a non-Fermi liquid. But within dynamical mean field theory, you'll always end up with a Fermi liquid. Okay. So the second result we found actually, Arthi actually found around the same time using iterated perturbation theory, but we didn't publish it, and then she went off for postdoc, then came back, and then we picked up the thread again, and then Soumen Bagh, my student, got involved, and we did a much more thorough calculation of the impurity problem here using quantum Monte Carlo, and you find that if you get actually if you allow for antiferromagnetic order, you get a first order quantum phase transition at some critical value of U, and this preempts the transition to this paramagnetic metallic phase. It's kind of an unfortunate thing because that paramagnetic metallic, a correlation induced metallic phase is pretty interesting. But it turns out that this insulating tendency in antiferromagnetic insulating tendency is too strong, and it preempts the transition. But nevertheless, there are lots of interesting aspects to these transitions, because the thermal transition from the antiferromagnetic insulator to the paramagnetic band insulator is first order for weak to intermediate 2, but continuous for large U. And you get a line of tricritical point that separates the surface of first order and continuous transitions. So this is the transition I talked about. There's a paramagnetic band insulator, and it goes into the antiferromagnetic insulator. Okay. And then this is the set of surfaces I was telling you about. There's a surface of first order transitions in this 3-dimensional space, and a surface of continuous transitions, and there's some tricritical point. There's a dome, the tricritical point. A section of that is shown for one particular set of parameters. Okay. So then, even the other interesting aspect we found is that within the antiferromagnetic state, the up and down spin particles have different gaps, and there's a range of U in which one spin gap increases with increasing u while the other one is decreasing, and there is a critical value of u where one spin gap vanishes and the other one is finite. So this is a correlation induced antiferromagnetic half metal, and there is like a quantum critical line in the phase diagram which I had drawn but I didn't draw attention to. So that's pretty interesting. So this is the evidence showing that there is a gap in the paramagnetic phase. Up and down have the same gap, and then the magnetic order turns on and you can see them breaking apart, and one of them continues down, goes to 0 at one point, the other one continues to increase, and that is that antiferromagnetic half metal point for one value of u, and there's a line when you change values of. Okay, so that's that dashed line there. Okay, so that's this, and then because you have these two different gaps for up and down spins, it's not hard to think about that if you were to dope it, you would preferentially dope one spin species and not the other, and therefore it's very easy to dope this system and get a half metal. At half filling, it is antiferromagnetic half metal at that one line, but that's very special line. It's difficult to access. But I'm saying when you dope it, it becomes a ferrimagnetic half metal with a non-zero net magnetization as well. Okay, all right. So that's the story as regards this nearest neighbor Hubbard model. So but we missed this tantalizing metal correlation induced metallic phase. So we thought let's look at model with frustration where we suppress the antiferromagnet and see whether we can stabilize the correlation induced metallic phase, and that the simplest such model is this TT prime ionic Hubbard model where I mentioned. And as you know, all of you know, if I take U large, this maps to a Heisenberg model with a first neighbor J and a second neighbor J prime, and that is well known to be frustrating for the antiferromagnetism. So the issue is, can this suppress antiferromagnetism enough to allow the formation of paramagnetic metallic phase? Okay, and the answer is it does. Not only it does that, but it does all kinds of spectacular things. So here is the phase diagram within the dynamical mean field theory and the CTQMC impurity solver for this TT prime Hubbard model. And here is this paramagnetic metal phase which I was telling you about, which is elusive for T prime equal to 0, because you can see T prime equal to 0, I simply directly go from the band insulator to the antiferromagnetic insulator, but just turning on a little bit of T prime is enough to stabilize this paramagnetic metallic phase. I'll tell you more about it as we go along. But in addition, you get all kinds of interesting phases now. You get a ferrimagnetic metallic phase even at half filling. Okay, and then you get an antiferromagnetic half metal. Remember, there was this sliver, one line of antiferromagnetic half metal inside the antiferromagnetic. So now there's a whole region which is a stable antiferromagnetic half metal phase. But eventually, if you make U large enough, you always get the mod insulating antiferromagnetic mod insulating phase. That's the phase diagram. And then this inset here is showing what you would get for this model if we did unrestricted Hartree-Fock theory, allowing for all these magnetic orders. And interestingly, all the phases that appear in this dynamical mean field calculation actually appear here, but for very different values of parameter regions. And there are some things which are qualitatively wrong, which is that this antiferromagnetic half metal phase seems to be stable for all the values of A prime, whereas that's not the case when you do full DMFT. It's for only a limited region where it's valid. Okay. So actually, in some sense, all these phases are actually adiabatically connected to these phases which you get from Hartree-Fock. And in fact, that gives you actually helps you to understand what is the nature of these phases. So let me discuss the Hartree-Fock theory a little bit so that you get a sense of what these phases are, where they're coming from. Okay, so if you do a Hartree-Fock decomposition of the interaction term as in the standard way, you will get two spin-dependent lower bands. You remember in the simple model, I had one lower band and one upper band in the band insulator. Now I'll get in principle two lower bands because they're spin-dependent and two upper bands. and that's the dispersion. So there's the T prime goes up front here, and there's a term depend on the ferromagnetic magnetization which adds to this. And then inside the square root here, there are two bands plus minus. Inside the square root, you'll see that basically the antiferromagnetism, the staggered magnetization, as well as the staggered density, which is the density difference between the A sublattice and the B sublattice, kind of renormalizing. In the presence of U, it's renormalizing this delta. And in the simple Hartree-Fock, you remember, that's the renormalization. If I turn off M sub S and M sub F, that renormalization is delta minus U delta N, which I talked about earlier. Okay, so that's the same. But now you have a much more interesting renormalization of this effective gap. And then now this upper band has a minimum at this K, these points, plus minus pi by 2 and plus minus pi by 2, these 4 points in the zone. And that is the value of that. And the lower band has a maximum at pi 0, 0 pi, these 4 points. Okay. And so it's an indirect band gap insulator. Okay. And now you can ask the question, what happens if you change these parameters? And here, okay, so then first of all you find that self-consistently there are all this magnetic order as a function of U that corresponds to that phase diagram. Okay. And for various values you can go up and you can see the antiferromagnetic, basically this is the line above which, sorry, that there is this line above which the magnetism sets in, and there is this region here, you can see where the ferromagnetism sets in and gets weaker and weaker, and then becomes 0 and then again sets in. And you can see that in this picture, the ferromagnetism increasing, decreasing, going to 0 and then again increasing. So that is that part of the thing. And the antiferromagnetism is setting in, and these lines actually indicate the full lines indicate first order phase transitions. Here is the first order transition, this line, these are like continuous transitions into the metal phase, and this is the first order transition. There's just a portion here which is a continuous transition. Okay. So all of those features are very easy to calculate from this thing. Okay, so how do you, so that's as regards to magnetism. How do you make out all these, whether it's metallic, insulating, etc.? So that is basically seen by just tracking these up maxima and minima of the two bands, and you can see here is the band insulating phase where the minimum of the upper band, and here there's spin degeneracy, you can see it's paramagnetic, right? And the minimum of the upper band is above the Fermi level, and the maximum of the lower band is below the Fermi level. That's a band insulator. But here you can see this is crossing over, right? This minimum is going over there, and this maximum is going above the Fermi level, that minimum is coming down below the Fermi level. So you can see basically you're going to generate electron pockets and hole pockets at these places where there were minima and so on. So if you are actually very strict, you should call it like a compensated semi-metal, but I'm not going to bother to do that. I'm just going to continue to call it as a paramagnetic metal. Okay, so that's that. And then you can see that at this order, when the magnetic, at this critical value of U, when the magnetic order sets in, these things split. And then, yeah, that's the ferromagnetic metallic region. And then you can see that for one spin species, if you track it here, you see this one, this green one is the downspin. Okay, that's the maximum of the lower band for the downspin that's come below the Fermi level. And similarly, the minimum of the upper band for the downspin has gone above the Fermi level. So that's completely gapped, whereas the other spin species is reversed. So it's still metallic in one spin channel, but not in the other channels. So that's the antiferromagnetic half metal phase. In fact, as soon as you have that, you can actually show that rigorously that it has to be antiferromagnetic, exactly. And then here, of course, I'm back in the antiferromagnetic insulating phases where there's a gap for both spin species. But you can see in any of these scales that one spin gap is very different from the other thing. So this will still retain that issue that I told you about, that if you were to dope it, you will get a half metal, but a ferrimagnetic half metal. Okay, so that's what that is. And you can also see this in the spectral functions, for example, which you can actually calculate very easily in the Hartree-Fock approximation. That's the antiferromagnetism thing, where one spin species has a gap and the other one has a finite density of states at the Fermi level. Here, antiferromagnetic insulator, where both spin species are gapped, and so on. Okay, but you can ask the question, how the hell am I going to see these metallic thing in this quantum Monte Carlo stuff? Because I only have imaginary frequency data. And it turns out, so if you were to do analytic continuation, it's pretty difficult to see all these subtle things. But there's a, so here is the CTQMC thing. You can see the same magnetic transitions and all that. So the way to do it, Sumilan did this with painstaking attention to detail with large sets of parameters. You calculate the momentum distribution function in the Brillouin zone, and you can actually calculate that just from the imaginary frequency Green's function that you calculate in this CTQMC. And you can see this, and this is actually the ferrimagnetic metallic phase. And you can see these electron pockets here and the hole pockets here, and different for the up and down spin species. And that's the ferrimagnetic phase. And you can, here is like actually a plot of it along some directions in the zone. And then here is the antiferromagnetic insulating space. You see, because if the system is insulating and gapped, this momentum distribution function is basically n of k is exactly half for the insulating thing. You can see here n of k minus half, basically this is basically half in the zone for the down spins, but it still has electron and hole pockets for the up spin, and that's the antiferromagnetic half metal. Okay, so that's how we got all the thing. Okay, so I have just 3 minutes, and let me end this thing with this. So you can say, hey, already interesting magnetic thing is that superconductivity in the strongly correlated band insulator, and the answer is yeah, most likely. Okay, and so I'm going to look at the very strongly correlated limit. So this attention was drawn to this first by a paper by Samantha and Rajdeep Sen Sharma in 2016. So they basically looked at this a model in this extreme strong correlation limit where U and delta are both much larger than the hopping in the simple TU delta ionic Hubbard model. Then if you go back and look at this atomic picture, you can see that on the A sublattice I can sort of throw these states, the doubly occupied guys out, project them out, and on the B sublattice I can project out the empty sites. So I can just work with this subspace of states on the B side and that subspace of states on the A side. Okay, and you can sort of introduce slave bosons for those of you who are familiar with it to discuss. So like these holons and spinons on this side, and doublons and spinons on this side, and use pseudo fermion and pseudo bosonic operators and with local constraints. And then so you can get an effective, this is like the analog of the TJ model for this model. Okay, and you can do slave boson mean field theory. And when they did that, they found that it looks like superconductivity is winning out in some region of this phase diagram. So that's okay. So we wanted to look at this in a very different way with using something called the Gutzwiller approximation, which is that actually these operators that arise in these effective Hamiltonians like TJ-like model are very, like they are projected operators, so they don't obey canonical commutation rules and all that. So you have to either go this trick, or there's another trick that Gutzwiller introduced long ago, which is you sort of convert them back to canonical operators by renormalizing the parameters that are in the Hamiltonian using something called the Gutzwiller approximation. So we decided to try that out because it's kind of very hard to make a connection between this stuff and what we've been doing in dynamical mean field theory. Whereas we found that when we did this Gutzwiller renormalized mean field theory, you could actually connect it to dynamical mean field theory. And here's like a benchmark. The same CTQMC thing that I showed you could be done for very large U delta in this regime. And you can see the staggered magnetization and the staggered, I'll just take 2 minutes. Staggered delta, the staggered occupancy are pretty much in correspondence between the two different ways of doing the thing. So, and then you can ask within this approach, you can allow for superconducting order parameter and then ask what happens. Then we find that for the TU delta model, there is superconducting order parameter possible, but it's always metastable. In the sense, the antiferromagnetism is always lower in energy than that thing. Okay, it never wins. Okay, but that allows the possibility that maybe if you turn on T prime, which suppresses the antiferromagnetism, can you make the superconductivity stable? And Anvesha has been doing this. So we haven't written up this, and this is what she finds. Actually, in this Gutzwiller-Renormalized mean field theory, you can see all the phases that we found in the DMFT at the lower values of U and delta are still here. Antiferromagnetic mod insulator, band insulator, paramagnetic metal, half metal, but there is a region of the phase diagram where you can actually stabilize D wave superconductivity. Extended S wave is actually very close in energy. So this system is very interesting because it's already superconducting at half filling. So maybe when you dope it, it's even easier. Maybe it'll make a high Tc superconductivity. Okay, so let me just leave you with those thoughts. So this raises lots of questions. Is this generic to strongly correlated band insulators with two inequivalent sites? Will these effects survive more accurate theories? What is the nature of the quantum phase transition? What's the properties of this paramagnetic metallic phase if you do a better theory? Is it non-Fermi liquid? What kind of metals are these? And lots of things. And are there materials? Is this for real? Are there materials which do all this? So, and this antiferromagnetic half metal is pretty interesting from the standpoint of spintronics, if you could make such materials. Okay, and then doping, does it give you all these fancy phases? So I hope my talk has enthused some of you to maybe look at this problem, because the attention that the community has given to this other thing is mind-boggling, right? Over the past 2 decades, we have so many investigations of that, but this one is lagging for attention. So, all right, thank you for your attention.
Questions?
Double Perovskite is perhaps the natural choice because there you actually have two sides.
Right.
You have possibility of strong correlation at both the sides.
I'm sorry, I had some slides on the thing that you and Prabhuda looked at, but I ran out of time. So, but I would actually like to see if I can get a stoichiometric material.
Yeah.
Because the sample that you found, I mean the thing that you found.
But we recently actually proposed some of the stoichiometry.
Oh, okay.
Stoichiometric one.
Then we should
really talk.
That'd be really nice.
Yeah.
Because already, I mean, what I've shown you is that many of these phases you can see, at least not the superconducting phases, but the magnetic phases, that is all the magnetic signatures of this already you can see in Hartree-Fock, which means in density functional theory you should see all this, and maybe if you take those and then make it superconductivity.
Excuse me. So in the phase diagram that you showed us of the TT prime ionic Hubbard model.
Yeah.
So there was before. This one. The one on the next.
Oh, that's the Hartree-Fock phase diagram. Yes.
Right. So the Hartree-Fock phase diagram, you are seeing some transitions which are second order.
Yes.
But it's a mean field theory, right?
Yeah, mean field theory, but even mean field theory you can get a second order transition. They won't get exponents right, but is that just saying, because these are second order for some of them are second order for a trivial reason, in the sense here this is second order or continuous because there's a gap which is opening up gradually. So you have to classify that, very low energy excitations here. And this is first order, but here we find that across this line, the magnetic thing turns on continuously. But these are like within mean field, you can understand it in terms of like Ginzburg-Landau with 4th order plus 6th order, and then the competition between 4th order becoming negative and 6th order. So those kind of within that picture, it'll fit into that framework. Yeah.
Thank you.
So I have a question regarding the strength of superconductivity when you turn on T primed.
Yeah.
So if I recall Rajdeep's work correctly, he had this very strong prediction that it scales as T literally. But is that the case that somehow it's scaling with kinetic energy scale T, or is it J again in your?
I am not sure. At least I don't. Okay, I have not looked at the data in detail. This is some very recent work, so we need to study that. How about how this thing scale and all that. Sorry, one more question. I mean, point, because remember this is in the TT prime, so there are two different, even kinetic energy wise, there are two different scales. Yeah, sorry.
Excitonic insulators.
Yes.
Ungap.
Yes.
They introduce interaction. Triplet excitons do come down. And some of these magnetic can be viewed as triplet exciton content.
Yes, that is true. But the thing is, at least, yeah, it's possible. But within my dynamical mean field theory, I don't know how to distinguish that. But at the moment, I'm saying it seems to be consistent with this thing being adiabatically continuous with Hartree-Fock thing, because, like at least hole pockets and electron pockets and all that. But I presume if it is excitonic insulator, it would be
Clearly the magnetic part.
very different.
Triplet. Because with some Akbar, my collaborator, we did some work. Like you take graphene and have A, B sublattice difference, like in hexagonal boron nitride. And then some of the triplet modes that were there in graphene comes down.
Yeah, so you're wondering, okay, so the issue is you're wondering that after whether the paramagnetic metallic phase with electron and hole pockets, you're raising the issue that will become insulating again, right? That's what you're raising, right?
Triplet excitons come down, they peel off, and there is an instability.
Okay, yeah,
depending on
so
this.
we'll
We'll
discuss
discuss.
that. I don't know how to build that into this as a separate thing, because at some level, at least at the level of, if it's included in local correlation physics, it should be inside dynamical mean field treatment, automatically included. But yeah, but it's an interesting question what you're raising about how to separate that. Yeah, I don't know the answer to that.
Right, in the interest of time, I think we should move on. So let's thank the speaker one more time.